but we got to get going. So what's going to happen the next time we're together, which is probably Thursday, we're going to have a quiz. And the quiz is going to be over problems like the ones we're going to do right now, okay? So you know, just from our one day of doing this, that the problems are all different. You have to read each one, but we've used similar strategies on them. So here we go. Number one, how many outfits can I make with 3 jumpers and 4 shirts if every shirt can be worn with every jumper? So in other words, there's no restrictions. What's the answer to that question? 12. 3 times 4. That's exactly right. You can choose a jumper 3 ways, and you can choose a shirt 4 ways. So 3 times 4. 12 different outfits. How many license plates can be made that contain 3 letters followed by 2 digits if no digits can repeat, but the letters can repeat? All right, what's that going to look like? 26. Okay, it says you can repeat letters, so won't this be 26, 26, 26? And then 2 digits, this will be 10, 9. Guys, there are 10 digits. Think of the numbers you learn as a child. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are your single digit numbers. There's 10 of them. So we're going to multiply all these together, and that would be the answer. On your quiz, you will actually multiply them together, but I'm not taking our class time to type all that in. But you will. You will have an answer blank. This is your work, and then the answer will be this big number over here. All right, how many, okay, this is like multiple choice. How many committees of 5 can be made from a group of 12? And the question here is, are you going to do it as a permutation, or are you going to do it as a combination? Combination. Why is it a combination? There's no order. If I tell you guys, okay, I'm going to pick 5 of you to serve on my committee, does it matter if I pick him first and her second? No, not if they're serving on a committee. When does the order matter? If I'm picking a president. That's right. That's exactly right. All right, so 3 is 12C5. Now what about 4? It's a similar problem. Now I'm giving away a calculator, a pencil, and an eraser. So I'm picking 3 kids out of 20. Is that going to be a P problem or a C problem? That's a P. Why is it a P? They're getting different prizes. It's like president, vice president, and treasurer, right? They're getting different prizes. Order matters. How many different, oh, here we go. We're getting ready for some probabilities soon. How many different 5-card hands are possible from a standard deck? That's a combination problem. That's a combination problem. Because when you're sitting there with 5 cards in your hand, does the order that you put the cards in your hand matter? No. So it's 52C5. Total number of hands. All right. Now, how many 5-card hands contain 3 diamonds and 2 clubs? So 3 diamonds and 2 clubs. You're going to pick a 5-card hand. It's got to have 3 diamonds and 2 clubs. Anybody have a guess? How many diamonds are in the deck?
All right, so at this point, everybody should have that written down or almost.
No, 13. There's 13. Guys, you might want to just look at a deck of cards because in probability, there's a lot of card problems. There's 52 cards in the deck. They're divided up into 4 sets called suits: diamonds, hearts, spades, and clubs. 52 divided by 4 is 13, so each suit has 13 cards, right? So diamonds and hearts are red, clubs and spades are black. So half the deck's red, half the deck's black. and then the cards have different values. So there's like an ace, and then king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay, so this question says, I want 3 diamonds and 2 clubs. So if I have my deck of cards here, I'm going to separate it into piles. There's going to be 13 in the diamond pile, and 13 in the club pile, and then there'll be 26 more cards over here that I'm not interested in for this problem. I need, from these 13, I need to pick 3. So that's going to be 13C3. There are 13 to pick from that are diamonds, and I'm going to pick 3 of them. And then there are 13, and I'm going to pick 2 of them from the club pile. Now, in forming a hand, the order of choice never matters. So whether I get the 2 of clubs and the 4 of clubs, or the 4 of clubs and the 2 of clubs, doesn't matter. The order I'm choosing doesn't matter when I'm putting them in my hand. Okay? Now, what am I going to do with those 2 numbers? I know how to type this in on my calculator, and I know how to type this in. What am I going to do with those 2? Multiply them. Because you are picking diamonds and clubs. That's the same as jumpers and shirts. So you're going to find these 2 numbers and you're going to multiply them, and that's how many hands like that there are. All right, let's turn it over because there's some more on the back that are good ones.
Ms. Fuller, how do you put 13C3 on the calculator?
Who remembers?
You go to math, you go to prop.
So math, prob, and down to NCR. You gotta put the number in first, so you gotta put 13 in, for your math step, please. And then the NCR button, and then 3. Yep. All right, number 1. I'm on the back side now, the back. How many 5-card hands contain exactly 2 hearts? 5-card hands, 2 hearts. Now, this problem is a little tricky because it's a 5-card hand, but they only tell you about 2 of them. 2 of them have to be hearts. What does that mean about the other 3? They're not hearts, right? I don't care what they are, they're just not hearts. So how many hearts are there in the deck? 13. How many not hearts then are there in the deck? 39. Because not hearts would be the clubs, the spades, and the diamonds. I need 2 of these, and I need 3 of these. So these 2 problems are almost identical. The second one I think though is a little bit harder because you have to figure out what those other 3 are, and they're not hearts. Anything but hearts. All right, how many ways can I distribute 4 identical pencils in a class of 20? Anybody have a guess on that? It would be 20C4. Very, very good, Grace. 20C4. Why is it a C and not a P? Because the pencils are identical. So if I give Michael his first and then George, it doesn't matter. They're both getting exactly the same thing. 20 kids, I'm choosing 4. And order doesn't matter. How many ways can a coach select a batting order for her softball team of 9 players? 9 factorial. 9 factorial. Because, oh, by the way, we haven't talked about this. Did anybody think 9P9? Go ahead and type that in on your calculator and see what you get. 9P9. That would mean 9 kids chosen all 9 in order. Does adding order, so you can do it as a permutation if you'd rather. It is 9 factorial. How many ways can 4 identical red, 3 different yellow, 5 identical blue be arranged on a shelf? Now, the key word here is the books are identical. So that's important, but not in the beginning. How many books am I arranging on my shelf all together? How many books? 12. 12 books can be arranged 12 factorial ways. Remember, if you are lining up n things in a row, it's n factorial. Period. Now, who remembers how we accommodate the identical, the duplications? Anybody remember? We did it with Mississippi yesterday. We divide. And we divide by each individual duplicate item. So we've got 4 identical red books. So we're going to divide by 4 factorial. Those are the red books. It's like having 4 R's in a word. Now, what about yellow? Am I going to divide by 3 factorial? No, because the yellow books are different. Maybe there's a bright yellow and a dark yellow and a gold or something. They're different. They're distinguishable. And then 5 identical blue books.
So you took the 3 anywhere?
No, the 3 is incorporated into 12, but it has no place individually because the books are different. Remember, when you're typing this in to get an answer, that's got to be in parentheses. Please do not forget, in any fraction that you ever do, it doesn't have to be this class, it doesn't have to be this material. If you are dividing by more than one thing, your denominator has to be in parentheses. How many ways can 7 people be arranged in a circle? 6 factorial. Remember, 7 people in a row is 7 factorial. 7 people in a circle is 6 factorial. When you arrange in a circle, it's always 1 less. All right, how many ways can 3 algebra students, oh, wait. We haven't talked, we're going to do this problem. This is what we haven't talked about yet, so we're going to talk about it later. But that kind of question will not be on the quiz. Okay, we'll come back and do it, but let's finish the rest first. How many ways can the letters of I love math be arranged? Oh my gosh. I just typed the quiz, and I think that's a question I typed on the quiz. That is that question. Yep, I'm going to have to change it. Okay. How many ways can those letters be arranged? How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll start with 9 factorial.
I think it's just 9 factorial.
Are any of them the same? No. Then the answer's 9 factorial. If there were 2 M's or 2, what? Oh, sure. If there were 2 of something, we divide by 2 factorial. 3 of something, we divide by 3 factorial. We don't have any duplicates. How many ways can first, second, and third place ribbons be awarded to a group of 10? Okay, I heard 10C3, 10P3. What do you think it is? It's got to be a P. It has to be a P because aren't the prizes different? Order matters. You want to be first. You do not want to be third. How many 5-card hands contain exactly 3 aces? Now, this is another one that's a little bit tricky. You've got to think about this. You're getting 5 cards. 3 of them are aces. What are the other 2? Not aces. Don't forget about these guys. All right? How many aces are in the deck? Remember, there's 1 per suit, and there's 4 suits. So you've got 4 aces, and you're going to choose 3 of them. And you gotta pick 2 not aces. How many cards in the deck are not aces? 48. Remember, there's 52 altogether. 4 of each kind. I mean, of each, like, label. So 4 5s and 4 queens and 4 aces. So you've got 4 aces, you're choosing 3, and times, you got 48 other cards and you're choosing 2. Is that okay with everybody?
So with the first problem we did, so why was it 13 and not 4? So like with like the first problem we only wanted to do.
Because that was hearts.
Okay, so I need you to take notes.
Aces are a label on the card. There's an ace of hearts and an ace of spades and an ace of diamonds and an ace of clubs. How many ways can 10 people be arranged around the dining room table? 9 factorial. 9 factorial. All right. So the quiz we take tomorrow will be that we actually just went through 3 of them. So it'll be a short quiz like these, and it will have problems on it like we have just now discussed. We're moving on, but it will have problems on it like we just discussed.
So are we supposed to know like how many cards are in the bag?
We will use a standard 52 card deck. Yeah, and you'll need to know how they're divided up.
So I have to know like how many aces, how many like, clubs and stuff.
But it's real easy because there's 13 cards in a suit, like 13 diamonds, and they're all different. I mean, there's not like 2 diamonds that are the same. There's a 10 of diamonds and a 9 of diamonds and an 8 of diamonds. So there's 1 of each kind in each suit. So that makes 4 of each kind, since there's 4 suits and you only want each kind. Yeah, it's not hard. And it's really considered kind of standard knowledge. I'm not sure. You guys never play cards? All right, so that takes care of that. Now, we're moving on, but anything we talk about now, these kind of new problems we talk about, are not on the quiz. The quiz, you want to practice some more, go back. These are exactly the ones, okay, that we just went over. I do want to do on that Precal A Period 4 is too cool quiz. Number 1, it says we have 3 algebra and 4 Precal students. And we're arranging them in a row, but the algebra students have to be kept together. Okay? So, I don't know what the official name of this is, but I call this bundling. We are bundling, we're arranging some stuff, but we're bundling a particular group together. So it's pretty easy how it's done. If I have these 7 kids in the room, and I say, all right, you 3 have to sit together, then what I've effectively done is tied a string around them and said, okay, wherever you guys sit, you are clumped together. So instead of functioning as 3 separate students, these actually function as 1, because I bundled them together. So I'm not arranging 7 things, I am arranging 5. So I start with 5 factorial, because I've got these 4, and then I've got this bundle that I tied together. But, remember when I tied a string around these guys? I could do that 3 factorial ways. So within the bundle, there are rearrangements. So I can have them sitting in this order, or I can flip-flop these 2 or those 2. So, we start with 5 factorial because there are 4 of these and 1 of these. So that's 5 factorial. But the bundle itself can be rearranged. So we multiply by 3 factorial, and that would be the answer to the question. Now, let's go to our notes, because I think that's the next thing on the notes. So back on my notes, and these pages are not numbered, but it's number 33, says 6 couples are arranged in a row, but each couple must sit together. So basically, you and your date walk into the movie theater and you gotta sit next to each other. And George and his date gotta sit next to each other. And Mr. and Mrs. Ford gotta sit next to each other. How many ways can we do that with 6 couples? Any thoughts?
So 3 factorial.
Now it's 6 couples. So we're starting with 6 factorial because the couples could be arranged that way. Okay? What about Mr. and Mrs. Ford? Can they be rearranged? We're tied together. We got to stay together. But couldn't he sit there and me sit here or vice versa?
Yeah.
So couple number 1 could be arranged 2 factorial ways. And what about couple number 2? Yeah. So there's the answer to the question. So the big idea is when these 6 couples come in, they're coming in as 6 units. And 6 units can be arranged 6 factorial ways. But each of the units can be arranged 2 factorial ways. 2 factorial is just 2, but I want you to get in the habit of thinking of it as factorial.
So then for those, could you do 2 factorial to like the 6th power?
Yep. Yep. Now, I have actually, honestly, I don't know that I've ever typed in 2 factorial raised to the 6th. I think it will work. I don't know.
Yeah.
I mean, that's what you're doing. Okay. All right, next one. Let's see if there's another one like that. How many ways can you, that's supposed to say, arrange 7 identical algebra books? So we have 7 identical algebra, 4 different geometry, and 3 identical trig books. All right, so here we go. How many ways can we arrange these in a row? Just arrange them in a row.
14.
Let's see, how many are there? 14, so we're going to start with 14 factorial. Do I have to modify that in any way, or is that my answer?
Divided by 7 factorial.
You got to divide it by 7 factorial, 3 factorial. Kids, you always have to divide by your duplicates. Okay? So there's no restrictions on arranging these books, but there are duplicates, and we always divide by the duplicates. So everybody clear on why it's 7 and 3 and not 4? All right, so that's A. In a row, if the books of each kind are kept together. Now think about that. That means you're bundling those, you're bundling those, and you're bundling those. So you're not arranging 14 things anymore, you're only arranging 3. So you're going to start with 3 factorial. But remember, when you bundle things, just like the couples at the movie theater, you have to multiply by the bundle factorial. So I'm going to multiply by 7 factorial, 4 factorial, and 3 factorial. But then I got to turn around and divide by 7 factorial and 3 factorial because I always divide by duplicates. So some of that stuff's going to cancel out, but that would be the setup. So let's make sure everybody's clear on this 3. Where did this 3 come from, this first 3? 3 bundles, right? And then the 7, 4, and 3 are each bundle because we multiply by the bundle factorial, the rearrangements within the bundle. And then where did this come from? Repeats, the duplicates. Yep. Yep. So if I were going to type this in, I'd go ahead and cancel that part out and not type in so much stuff. All right. Only the algebra books must be kept together. So only the purple books have to be kept together. Everything else is flexible. What do I start with? 8 factorial, very, very good. 8 factorial. Why am I starting with 8? Because that counts as 1, and then I have 4 and 3. 8 factorial. Do I need to multiply or divide by anything? I gotta multiply by 7 factorial because that's a bundle. And then divide by 7 factorial and 3 factorial. So if you're struggling with all this, just stop. You gotta multiply by bundle factorial. So anything that you've bundled has to be multiplied by that number factorial. So when I bundled my couples, each one got multiplied by 2 factorial. And then you always, anything that's identical, you divide it out. Now, we're going to evaluate by hand because there are little formulas for permutations and combinations. And if your problem doesn't have numbers in it, if it has letters in it, then those become necessary. So let's go ahead and evaluate this by hand, 10p3. Go ahead and type it in your calculator and tell me what it is. 10p3, so I know what answer I'm shooting for. And then I'll show you how easy it is to get that. 720. Now, if I'm doing this by hand and I don't have a calculator, it's going to be 10 factorial divided by 7 factorial. Now, I'm not typing that in on my calculator. 10 factorial is this. And 7 factorial is this. See how you get 720? Everything cancels after the 7. Or from 7 on, everything cancels. Now, where did these numbers come from? Well, I think it's obvious where the 10 came from. Right, that's that number. Where did the 7 come from, do you think? You subtract them. So in general, my formula would be n factorial divided by n minus r factorial. So if you had to do this by hand, it would be 6 factorial divided by 2 factorial. And then combinations, that's the same thing. Yep.
Is 6 factorial over 2 factorial the same as 3 factorial?
No. 6 factorial, that you cannot do, no operations work with factorials. Remember, this is 6 factorial, whoops, and this is 2 factorial. So it's going to be 30 times 12. 360 is what that's going to be.
Okay.
Okay? Yeah. That can't be simplified. That has to be worked out. There's no canceling is what I mean. Okay? All right. 10C3. What's that answer? Anybody got that one? 10C3 one? Is it 120? Okay. All right. Now, what would that look like in terms of a formula? Well, it starts the same way. It starts exactly the same way. But there's an additional 3 in the denominator. 3 factorial. So I took the 10 and then subtracted them, but then I have to include that number. So your formula is n factorial over n minus r factorial, r factorial. Okay, so let's try a couple by hand just to make sure you got that down. I'll leave the formulas up there for you. If you had to do 7C3, what would that setup be? If you were doing 7C, this is an extra problem I'm just throwing in. What would that setup be if you didn't have a calculator? Just see. So we'll start with 7 factorial, and then we'll subtract, so we get 4 factorial, and then we'll use that number, so we get 3 factorial. That's what your formula tells you to do. Start with that number, divided by the difference, and that. Now, if I'm not using a calculator, you can do this. It's 7, 6, 5, 4, 3, 2, 1 over 4, 3, 2, 1 and 3, 2, 1. Can you see a bunch of stuff's going to cancel? It always does. So that's all gone. The 4's gone. 3 and 2 goes to the 6. What's the answer to the problem? 35. 35, yeah. So it's not hard to do by hand if you have to. Would you do that for me? Same thing. Wait a minute. Well, first of all, it makes sense from a formula aspect, doesn't it, that they're the same? Just from the formula? But can anybody explain what's going on there? Why that would be from a practical, I mean, you know, like, I have a 3 and a 2 here. Think about this for a minute. 7 kids in the room. All right? And I say, I'm going to take 3 of you camping. I'm going to take 3 of you on a camping trip. All right? So I grab 3 of, there's 7 kids in the room. I grab 3 and I take you out in the hall. What's left in the room? So if there are 7 kids, isn't the act of choosing 3 automatically going to choose the other 4? Because you got the chosen 3, but you've got the unchosen 4 that are another group. So with combinations, it will always be the case. If you had 8C3, that will automatically be 8C5. Because if you have chosen 3, you've automatically grouped the other 5 as the unchosen. Now that's going to be important here in about 30 seconds. Well, if I get that fast. All right, so kind of just hang on to that thought. Okay? All right, now we're moving into something that looks totally different, but it is related, I promise. But it surely doesn't look like it. We're going to spend a couple minutes doing what's called binomial expansion. You'll see why very shortly. All right, so the first thing I said, let's expand. All right, so x plus y to the first. You don't need a teacher to tell you that's x plus y. What about x plus y to the second? You've done that a lot of times. Anybody remember what that is? Foil it out, what do you get? X squared plus 2xy plus y squared. And again, this is a FOIL problem. X plus y, x plus y. Now this one you probably haven't done as much. to have it memorized, but that would be x plus y times x plus y times x plus y. So basically it would be these two times each other. All right, well, you can just write this down. You don't need to figure it out. That's going to be x cubed plus 3x squared y plus 3xy squared plus y cubed. Now, if you are at all thinking, oh my gosh, Mrs. Ford, you're smart. I'm not. There's a trick, and I'm getting ready to show it to you. So the next one is x plus y to the fourth. You could just write this down. It's x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Oh my gosh. So now you're going to help me do x plus y to the fifth. Because I really don't want to multiply x plus y times itself 5 times. That would take a long time. Obviously, I don't have this memorized. There's something going on here. There's a pattern, and I need you to help me do this one. What do you notice? Maybe you can't do the whole thing, but what are some pieces you notice about it? Okay, so what she's saying is I'm expanding to the 4th power, so this is x to the 4th. And notice on the other end, it's y to the 4th. So you know, probably, that this is going to have an x to the 5th here and a y to the 5th here. Everybody else see that? Well, tell me about the x's and the y's in the middle of the problem. What's going on here, and then here, and then here? What do you notice there? Maybe look at one letter at a time. What's happening to the x's as we go from term to term, left to right? They're going down by 1. So whatever this term is, it makes sense it's going to have an x to the 4th. And this one will be x cubed, x squared, and x. And then there's no x at all in the last one. Does that kind of make sense to you? Okay. And then what about the y's? Do you see a similar thing happening with the y's? But yes, from the other way. So y to the 5th, this one's going to have a y to the 4th. And then there's no y on that first term. Now, does everybody see that that's what's happening in the problem? That will be what always happens in the problem. The power on the first variable will always start out, whatever the power is, and then it's going to decrease one at a time till it gets down essentially to x to the 0. There's no x down here. And then the y's do the same thing from the other end. You'll notice, by the way, that if I add the exponents in each term, you notice what happens within each term. The exponents add up to 5. Now, the numbers in front are the ones that gets a little bit confusing. So I'm going to just make a list of the numbers I know for sure, and then we're going to see if we can figure out what these numbers are. I'm talking about the coefficients. So I've got 1 and 1, 1, 2 and 1. I'm just writing down the coefficients. 1, 3, 3 and 1, 1, 4, 6, 4 and 1. Now those are the coefficients so far. I am wondering, what are the coefficients in this next row that will serve these numbers? Well, I think there's a 1 and a 1. That makes sense to me. 5? You think this is going to be a 5 right here? And probably down here too? That makes sense to everybody? Now what about those ones in the middle though? I need 2 of them here in the middle. 12 is a great guess, not quite right, but a great guess. This triangle is called Pascal's triangle. Anybody ever study computer language called Pascal, or ever heard of the language called Pascal? Anyway, he was a real smart guy. And this is called his triangle, and here's how it's built. This 3 right here came by adding the 1 and the 2. And this 6 right here came from adding the 3 and the 3. So the number that's going to go here is 10, and the number that's going to go here is 10. So these are 10s. If you needed the next row of the triangle, it would start with a 1, end with a 1, and then this number would be a 6, a 15, a 20, a 15, a 6. Everybody see how I'm doing that? You keep it organized. Then these 2 add to this one, these 2 add to this one, and so on and so on and so on. So this, I don't know, pattern will give you the coefficients on your expansion. Now, this is for, what does this have to do with anything that we've been talking about? Well, would you take your calculator out? And would you type in 6C4? 6C4. And 6C5 and 6C6. We'll just do that many. Would you type those in? What's 6C6, 6C5, 6C4, 6C3? Let's type those in. Tell me what you notice about those numbers. Which ones have you got so far? 20 is 15. Oh my gosh, wait a second. 1, 6, 15, 20. Where do you see that on the board? Pascal's triangle, those numbers are the combination numbers. If you did 6C2, you would get 15. If you did 6C1, you would get 6. And if you did 6C0, you would get 1. So if you wanted the 7th row of the triangle, but you didn't want to build the whole thing, you would do 7C7, 7C6, 7C5, and so on. And those would be your coefficients. All right. I don't even know why some of you look like you're bored. This is so cool. All right, let's try 2A. This might be the last one. I'm not sure how many more we'll get done. We're going to try. Let's see. Oops, I just erased my triangle, but you have it written down. All right, here we go. X minus 2y to the 4th. All right, so here we go. This is to the 4th power, so my coefficients are going to be the 4th row of the triangle. So I'm going to write down 1, 4, 6, 4, 1. Now, I just erased that triangle. You probably have those numbers written down. But if you don't, remember 4C4, 4C3, 4C2, 4C1, 4C0. That will generate those numbers if you don't have the triangle or don't want to build it. Next to each of those numbers, put the 2 components of your problem. Now, for me, they're x and negative 2y. In our last example, it was a plain X and a plain Y. But now we've got an X and a negative 2Y. Now we're going to put our powers on. Well, you already observed. What is the power on X going to be in this first term? 4, and then 3, 2, 1, 0. And then 4, 3, 2, 1, 0. So we figure out our coefficients, and they come from this row of Pascal's triangle. Next to each coefficient, we put the two pieces of the problem, and then we put our powers on. Now, these are individual terms. I'm going to put big plus signs in between, and I'm going to simplify each term. Sometimes we get confused because we see this and we think we're subtracting. No, this is all multiplication. This is a multiplication. It just happens to be a negative number. What does this simplify to? When we multiply all that together, what do you get? X to the fourth. Very good. Why is it x to the fourth? Anything to the 0 power is 1. So that's just x to the fourth. All right, now what about this guy? What is this one? This is a multiplication. What is it going to multiply to? Negative 8 x cubed y. Now be careful on this one, because remember when we put that negative 2y down, because that was this piece of the binomial, you're squaring that whole thing. So this is not a negative 2, it's actually a positive 4. So this is 24 x squared y squared. Because when you put down that negative 2y, whatever power, it goes to both. What about this one? What's this one going to be? Well, that's not a negative 2. It's a negative 2 cubed, which is a negative 8 times 4. So it's a negative 32 xy cubed. And what about on the end? It's going to be a 16y to the fourth, a positive 16y to the fourth, because that's 1, and that's 1. And that's your answer. All right, we're going to do one more because it's small, and it's the last one in this section. So here we go, 2x plus 3y to the third. Where do I start? What am I going to do first? Who can tell me? Get my coefficients. And where are my coefficients going to come from? The third row of Pascal's triangle, which is a very small row. So it's 1, 3, 3, 1. That's the third row. Now what? Put the two components. So this time I'm going to have a 2x and a 3y. Guys, remember to put them in parentheses. The 2x and the 3y, separate parentheses. Those are the two pieces of my problem this time.
And create your final draft in class on Thursday.
Then what?
My notes and your peer notes. How many
Exponents. And remember that the first one, in this case 2x, is going to start with a 3 and count down.
So we all know there's work.
And then the y's, same thing. And then each term is separated with a plus sign. And each term is multiplied. Multiplied. So this is all multiplied right here. So what is that? 8x cubed. That's it, 8x cubed. Because anything to the 0 power is 1. Here, be very careful. We got a 3 and a 4x squared and a 3y. So 36 x squared y. Again, be careful here. Got a 3 and a 2x and a 9y squared. Some of us forget about this, squaring this 3. Make sure you're squaring the whole parentheses. What is that, 54? xy squared? And then on the end, 27y cubed. That's just 1, remember? And there's your answer. You gotta admit, as bored as you all are, that's pretty slick. Pretty darn slick.